Welcome everybody to lesson 1. We're talking the fundamental accounting principle, which is part of combinatorics and discrete mathematics. Lots of applications, cryptography for all you spies out there, as well as a lot of computer applications. We're going to start off with a little investigation involving some food, and hopefully you're not hungry at this point, because there's a couple of examples with food. But we're going to look at different menu options available. We've got 2 types of sandwiches to choose from, 3 drinks and 2 desserts. We can organize this information into a tree diagram, which going back to grade 8 you should remember having worked with. We've got our egg or ham sandwich, which I'm sure are favorites with you. Then move on to drink, and 3 branches coming off of this. Branches, trees, get the theme. So milk, juice, coffee, egg and coffee. Wow. Have to throw a breath mint in there as well. And then finally with the dessert, we've got 2 more options here. So for the dessert, we have yogurt or pie. Try and draw these as quickly as possible, but I think you get the idea. Now the branches in the bottom row tell us how many options there are for us. When you count these branches, you see that there are 12. Those are how many meals are possible. And again, back to grade 8. We looked at this in grade 8, going back to Mr. Chung, Miss Armstrong, Mr. Nami. I did tell them, you know, sometimes these kids don't remember it in grade 12, so try and speak loudly. Unfortunately, only one of them listened to my advice. You know which one. Okay, we could also list these, and I'm going to list 2 of these, but I'm not going to list them all. So egg, milk, yogurt. This would be this branch right here. Okay, that's one of the 12 options. I think you get the idea. Let's not list them all. Going down to part C. How can you determine the number of possible meals without listing all of them? Well, if we go back up to what we were looking at here originally, we have 2 options for sandwiches. We have 3 for the drinks and 2 for the desserts. And if we multiply down here, we get an answer of 12. So we don't really need a list or a tree diagram, but do understand that sometimes those lists will be helpful in terms of answering things, as well as the tree diagrams. Some of the hardest questions we're going to look at this chapter will involve tree diagrams, so don't think it's too babyish. All right, example 2 again with food. Cafe features 24 flavors of ice cream. You can order 3 types of cones, regular sugar waffle. Suppose you order a double cone with 2 scoops. How many choices of cones? Well, we've got 3. How many choices of flavor for the first scoop? 24. How many for the second? Well, let's say 24 again. That will include then people that just love one flavor. Like myself, I'd probably go double Rocky Road on the waffle cone. I could really use one of those right now. How many different cones are possible? Well, fundamental accounting principle says it's 3 times 24 times 24. And off memory, I believe that is 1728, but don't quote me on that. Okay, a lot of different cones are possible. Okay, moving right along here. Sort of formalize this. Fundamental accounting principle says if one item can be selected in m ways, the next item in n ways. How many ways can the 2 items be selected? That'll be m times n. Don't really need that dot in there, but just want to reiterate that we're multiplying those 2. Okay, examples. We're off to university soon. Guys are heading off. Almost all of you, except for you grade 11s, you're stuck here for another year. Okay, using a tree diagram, we'll load in the colleges first, and we can just talk about those colleges: C1, C2, C3, C4. I'm not going to name them. I don't want to name Langara and all of these different colleges. And then the universities, we will just list those as U1. Doing that again. List those as U1, U2, U3, U1, U2, U3. I think you get the drill here. So I'm just going to write out the other three branches. And again, along the bottom row of those branches, 12 branches. That tells you how many there are. Using the fundamental counting principle, there'd be 3 times 4, 12 different options for post-secondary. Okay, question 2. Why don't you try that one? Pause the video. Just take a second to do that. I'm going to write down the answer though. Pause it now. We'll do number 3 together though. How many 3-digit numbers are there where 0 is in the tens position? Probably seen these types of questions, maybe on a contest. You know, this type of math really is approachable by students in younger grades. We're really just multiplying and adding. You'll see later we might have to do some subtracting as well, but you can handle it. 3-digit numbers where 0's in the tens position. Okay, I'm going to do boxes for the number of possibilities. The box, 3 boxes. This would be the hundreds digit. Yep, that says hundreds. Tens and ones. Okay, well, we've got 0 stuck here. That is one option. So we can put the 1 in there. Hundreds, now, again, a 3-digit number cannot start with the 0. We wouldn't say 0, 2, 3 is a 3-digit number. That's 23. So there's only 9 digits for the hundreds position, 9 options. For the ones, though, we do have all 10 digits at our disposal from 0, I almost wrote 10, 0 to 9. That is 10 digits. We multiply out and we get 90 different numbers. Okay, not really surprising. 99 minus 10 plus 1 would also give us that, but here's using the fundamental counting principle. All right, why don't you try number 4? Same type of question. Just pause it for a second, give it a try. Remember, in the English alphabet there are 26 letters. Occasionally you get a grade 12 asking me about that. And numbers, there are 10 digits again. Pause the video, try it. Okay, welcome back. The answer here should have had whatever 26 cubed times 10 cubed is. Okay, 26 times 26 times 26 times 10 times 10 times 10. And I don't know what that answer is. It's too big for me to do in my head. More importantly, I don't really care. All right. Houses in a fictional city have an address that consists of numbers. How many possible addresses could there be if the address could be up to 5 characters long? There's no such thing as house 0. Okay, well, up to 5 characters long means that it could be 1, it could be 2-digit, 3-digit, 4-digit, 5-digit. But really, Miss Jameson gave us a lot of space, but think about this. We have numbers, here we go again. We have numbers from 1 to 99999, 99,999 available to us. How many numbers is that? Well, without too much math, I believe that's 99,999. We're done. Okay, we could do this with what we're calling case analysis. We'll look at that later. I just don't think it's really important to use that here. I would hope you wouldn't use that method for this question. Don't tell Miss James. How many 2-digit numbers can be formed from these 5 digits? Okay, so you only have these 5 to work with. Repeats are allowed. So the tens digit, again, the 0 is involved, so we only have 1, 2, 5, and 9 available to us. So there are 4 numbers there. The ones digit, we do have all 5 digits available for this one. Instead of writing them out, I'll just do that. So we've got 5, and multiplying those out gives us 20 digits, or 20 numbers that we can make. Now, what about no repeats allowed? There's a few numbers in this 20 that would involve repeats. What are they? Well, 1 would be a repeat. 22, 55, and 99. Those ones are not going to be included in the second set. Now, how can we get our answer of 16 using the fundamental counting principle? Well, we go back to the tens position, and we would have that number still being the same. There's still 4 options here. It's this box that is a little different. And based on what we're looking at here, it doesn't take a brain surgeon to figure out it probably is 4. But how do we get 4? Well, without repeats, we've locked in one number here. Let's say it's 1. Maybe 1's been locked in. We add 0 now, so now we've got 4 numbers that remain that can go in this position. So 4 times 4 is 16. Okay, number 7. Using the numbers 1, 2, 3, 5, 6, 8, 0 with no repetition. Okay, that's important. How many 4-digit numbers can be constructed? All possible are to be considered. The number is even. Okay, why don't you try A on your own? I'm going to change color of pens. Pause the video. Try it. And then we'll look at it. All right. So for all possible to be considered, we have 4-digit numbers. Again, 0 is not available to us in the lead position. So for this one, we can use anything but 0. So that gives us 6 numbers here. We then eliminate one of those. So again, let's say maybe it's 1 this time, but we bring in 0. So we subtract 1 but add 1 for this next one. So we're back to 6 numbers. From here on, we are dropping 1 number and right down to 4. Multiplying those out, 7 to 0. 36 times 20, that looks right. All right, the number is even. Okay, here's where we're going to use some case analysis and talk about why that is. What determines an even number? Well, it needs to end in 0 or 2, 4, 6, or 8. Well, we've got a few of those options. We've got 0 as one of the numbers. So the problem here is that because 0 can't be the lead digit, it's going to have a different number of answers than the other even numbers. So case 1 ends with 0. All right, well, in this case, we have only one option here. Okay, we're putting 0 in here. Now, what about the other 6 numbers? We're going to go back out to the thousandth position. Any of those 6 can go in here. So there's 6. We drop 1, we get 5. Drop another, we get 4. We multiply, we get 120. So 120 numbers that end in 0. What's going to be the other case? Well, we could do a case for each of the possible endings, but the numbers that end in non-zero numbers will have the same number of cases. So we can combine those into one. And I have to remember what numbers we have. We've got 1, 2, 3, 5, 6, 8. So 6 and 8 are numbers here. So case 2 ends in 6 or 8. Now in this case, we have 6 or 8 here. So there are 2. Whoops, I'm missing one, aren't I? Or 2. Or 2. Missed that one. So there's 3 here. Now, we go back out to the 1,000 position because we can include the 0, but the 0 is still part of the mix. So here, we've used one of the numbers in the ones position. 0 is not available to us, so we have 5 here. Then we pick up 0 again, but we've dropped one here, so we stay at 5. And finally, we drop 3 numbers. We're left with 4 here. So we get that, and then times 3. When we multiply that out, we get 300. Now, understand that of those 300, just by symmetry, 100 would belong to 2, 100 to 6, 100 to 8. So fewer numbers for each of these because the 0 can't be in the ones position. Now, these cases are not counting any, there's no overlap, they're not counting the same numbers, so we add the answers for each case, and we end up with 420. Okay, 420. All right, part C, each digit of the number is even. Well, in this case, we are now down to our 4 even digits, 0, 2, 6, 8. We basically get to just ignore the other 3 numbers that are odd. And again, we'll start with the 1,000th position. We only have 3 numbers that are available, 2, 6, or 8. Then we're back to 3 because we've lost one in that first position. We picked up the 0, down to 2, and down to 1. And multiplying that out gives us 18 numbers. Now here's another one where it would maybe be worthwhile just taking a look at a tree diagram for you visual learners. What's happening here is for that first digit, and again, I'm not going to do the whole tree diagram here because I just don't want to, but for the 1,000th position, we have 3 branches, 2, 6, or 8. Okay, no 0. For the next branch, the hundreds position, we also have 3. Okay, so this is hundreds here. In the case of 2, we've brought in 0. Whoops. We have lost 2, so we've got 6 or 8. Here we've got 0, 2, or 8. And here we have 0, 2, or 6. Okay, again, because there's no repetition allowed. Then hopefully you can see that there'd be 2 branches coming off of each of those, and then a single branch coming off of each of those for the one number that remains. Okay, and that would give us, so here, I'm not going to write in the missing numbers, but we'd have these. Notice that there's 18 branches at this point, but there'd be 1 more branch coming down for that 4th number off of each of these. You get the idea. Okay, moving down here. Divisible by 5. Divisible by 5. Number is divisible by 5. Again, 2 cases ending in 0 or in 5. Why don't you try this one? Give this a shot, and then, so pause it. Then I'll write out the answer here quickly for you, and we'll push on to the end. Okay, so case 1 ends in 5. Okay, numbers divisible by 5 end in either 0 or 5. So those that end in 5, five's here, so this is 1. Then we go back out to here. We can't have 0, so we've got 5 numbers here. We pick up 0 times 5 times 4, and we end up with 100, which is not too surprising, as the numbers, those were the same that ended in 2, 6, and 8. Case 2, it ends in 0. And the cases here, okay, again, it will finish with 1. Why 1? Because 0 is locked in there. Go back out here now. All 6 numbers are available. 5, 4. We've actually done this one before, right? We've already looked at ends in 0. This is 120. We're going to add those 2 sets of cases for a total of 220. All right, how many 4-digit numbers greater than 5,364 are possible using these 6 digits if no repetition is allowed? All right, pretty crazy question here. We'll thank Miss Jameson for that one. And doing this here, as we take a look at this, we are going to need some cases here. Now we're kind of looking at the lead numbers. Nice thing Miss Jameson did for us is we don't have the number 0 in here, so we don't have to worry about cases where it could be starting with 0. But this one, think about if for case 1, if the number actually starts, oops, case 1, the number starts with a 7 or 8. Doesn't matter what follows it. We are going to have all numbers that start with 7 or 8 will be larger than 5,364. Okay, so here's our first case. So 7 or 8, there are 2 options here. No restrictions for any of the other positions. We've got 5 remaining numbers. We've locked in one of those. So 5 times 4 times 3. 10 times 12 is 120. There is case 1. Okay, what is case 2? Anyone? You in the back. Well, we've got one other scenario that's kind of scary, and that's where it starts with 5. Ms. Jameson wasn't that kind to us in that she did put 5 in there, and 5's the lead number here. It would have been so nice if 5 wasn't there. Why? Why does 5 have to be there? Starts with 5. Now in this case, we actually do need 2 subcases. I'm sorry, but I'm really apologizing on behalf of Miss Jameson. We need to look at that next digit because notice if the second digit's 3 in the number that we need to be greater than, and if that number is 3, then we've got to consider some other cases. So we're gonna say that the hundreds value is 7 or 8. Okay, so this is now I'm running out of space here. This is going to be a 5, so 1, 7 or 8, so 2 options there. And then for the remaining numbers, it doesn't matter the order. So we actually have 4 numbers remaining, so 4 here, 3 here. Multiplying those out, we get 24. Okay. The other case, though, is where the hundreds value is actually 3. Okay, in this case, we actually have 5, 3, and then what are we left with? So 5, 3, this is 1, 1, only one way of doing each of those. Well, here, this number now has to be 7 or 8 to be bigger than the target number. So there's 2 options there, and that leaves 3 numbers. It's getting messy for the last one for a total of 6. So now we're just going to string together these 3 numbers, add them up, and that'll be 150. So 3 cases really, but hopefully you see why I did subcases for case 2. If you didn't, ask your teacher. Okay, we are going to finish this thing off quickly. If I can figure out how to scroll this thing. Oh, this is just the bane of my existence. True, false quiz. Left out the word quiz. You're forgiven, Miss Jameson. Has 7 questions. Suppose students answer each question by guessing randomly. How many possible answers are there for each question? Well, true, false, there's 2. T or F. How many different patterns are possible for answers to the 7 questions? Well, this one, be careful. You're not just multiplying 2 by 7 here. Just because you see 2 numbers doesn't mean you're going to do this by multiplying those 2. Here's question 1. There are 2. Question 2, there's 2. Question 3, there's 2. We're going to multiply out 7 factors of 2. So in fact, the answer to this one is going to be 2 raised to the 7, or 128. Now, what's the probability a student answers all 7 questions correctly? There are 128 different answer keys that are possible. If we're assuming they're all equally likely, here's an example of one of them. Please don't go beyond 7 letters here. Okay, here is one of them. Well, let's say that's the one you choose. That one has a 1 in 128 chance of being chosen. That's less than 1%. Now, I know you guys have never guessed entirely on a set of questions, but if you did, less than 1% chance you'd get a 7-question multiple choice quiz aced. Okay, number 10, very similar, except now we're looking at 4 possible answers with multiple choice. I'm going to leave that with you to try, and we'll say goodbye from here. The answers are just below, and good luck with the worksheet. It's a doozy. Miss Jameson has come through big time.